an analysis for the IAXO pathfinder system. So we've heard about the pathfinder system already, and we're going to hear more details. Thanks, Cristina.
Okay, thank you, Julia. So, well, thank you for coming, and thank you for the organizers to give me the opportunity to talk here about the data taking analysis of the IAXO Pathfinder system. As Julia said, I am a PhD student at the University of Zaragoza, so this is the core of my PhD thesis, which I haven't finished, but more or less here everything is condensed. And well, of course, it's only me speaking, but we are a very big group, not only the IAXO collaboration, but the micromegas detector group. So, well, we start with a quick introduction about axion helioscopes and the current state of the art. We already heard a little bit about this from Esther the other day. We will hear more about it with Julia. But well, to do a quick summary, even if you already know all this, but the concept of axion helioscopes is that axions are produced in the core of the stars. They can travel freely to Earth and arrive here. And if we put a magnetic field, they may turn back into photons, into X-ray photons, because the expected energy spectrum of the axion flux, of solar axion flux, has this shape. So as you see, has a peak at 3 keV, average at 4. So this corresponds to X-rays. So we put an X-ray optics. It was not done before. It's done now, and then we focalize this into a readout, a detector. So a positive signal would be an X-ray excess when the magnet points towards the sun, versus when it's not pointing to the sun, so in not sensitive axion conditions. So this is the main layout description. The figure of merit that we try to optimize, we want to maximize it, has different terms. The magnet is important, for example, its magnetic field, its length, and its aperture. The other day, in fact, we had a question about how big the bores would be and the aperture, so we really want to maximize this. The efficiency of the optics, of the time data taking, and what I'm going to focus in this talk, which is the detectors. It's very important to have the highest possible efficiency and the lowest possible background. So, okay, the current state of the art is CAST. So the CERN Axion Solar Telescope, which is, it has more than 20 years of experience. It has given the collaboration more than 20 years of experience. To date, is the most powerful helioscope that we have, but it uses a decommissioned LHC dipole prototype, which is 10 meters long, which was not optimized for axion searches. Still, it has been a very good way of testing all the technologies and already imposing a very restrictive limit to the axion to photon coupling, which was done in the data taking of 2013 to 2015 with the IAXO Pathfinder system, and with the sunrise detectors that are positioned on this side of the magnet. There were also detectors on the other side, so that we could track the sun at sunrise and at sunset. That work was able to push this limit lower than it had been before. But now what I'm going to focus in this talk is this new data taking between 2019 and 2021, again with the IAXO Pathfinder system, but with some improvements. So until now, the typical results we were getting with argon-based gas mixtures had looked like this, the background spectrum. Oh, this is, okay. So we have a background, but based on the topological signature of X-rays, so we are able to select events that are X-ray-like and not X-ray-like. So if we filter them, we can reduce the background already by a few orders of magnitude, and we end up having fluorescence peak of copper at 8 and 8.9 keVs, and an escape peak of argon, which is the gas we have inside our chamber, at 3 keV. What's the problem here? That if you remember, if we see the expected solar axion flux, it precisely has a peak at 3 keV, which is where we have our big contamination from argon there. So if we want to improve our results, we really need to reduce the background in this energy range. So the motivation for this new data taking campaign, it's not only increasing the statistics, which before we had about 390 hours of solar tracking, now we have 300 more hours. So this will help us improve the sensitivity in the action photon coupling, as we can see in this plot, we had 0.66, and from about 7 months of tracking, which is the equivalent of 300 hours, we might be able to lower it to below 0.62, or in general to increase this sensitivity. But most importantly, the aim of this data taking campaign was to do research and development for IAXO and baby IAXO, so to gain experience, to learn how to use xenon-based gas systems instead of argon, which have to be operated in closed loop, as we will see later, to gain insights into the limitations of our energy threshold and our background limits, and also provide technical and operational experience that we will be able to apply to baby IAXO and IAXO in the future. So it's also helping us reducing risks towards IAXO and baby IAXO. So as you see, we did 2 different periods of data taking campaigns with the 2 different gas mixtures. The background time is very high. We have like more than 6,000 hours. And the action sensitive conditions sums up to 300 hours. So in principle, the statistics is nice. So not sure if I understand the question. Yes. Yes.
Is the magnet off the background?
Well, the magnet is not necessarily off, but it's not pointing towards the sun. So yeah. So to be in action sensitive conditions, we need both pointing to the sun and magnetic field to be on. So yeah, during background, sometimes it was on, sometimes not. The magnet, it depended also on other detectors if they were taking data or not. But for us, we really need to be tracking the sun, otherwise we wouldn't see anything. So how was all this done in practice? It's going to be a very experimental part. So sorry for the theories. I'm going to talk about the hardware, or how we were using the helioscope and we installed everything. So here we see casts that we already saw it before. In this data taking campaign, we were only using the sunrise detectors, which are positioned on this side, which are able to follow the sun during 1.5 hours per day during sunrise. And so the sun is here, the actions would come through the bulb, might turn into photons. And here we have first our X-ray telescope. So here you can see the end cap of the magnet, so this metallic part. So here we have the X-ray telescope, and then the photons would come here through the pipe and into our chamber, into our gaseous chamber. The telescope, the X-ray telescope, was not, it's just a segment. So the focusing of the signal has this shape, but we don't really care about the shape. We just care about having individual events in the smallest area possible. We also have shielding, both passive shielding, which is a structure of 10 centimeters of lead around the detector, and an active shielding, which in this case, it was a plastic scintillator to detect cosmic rays. So this is how we implemented it there at CAST. We have some more pictures. So here you can see better all the line, and here the connection to the electronics of the readout, so that here's our readout that we will see later, and all the connections come here that go to the computer. Here again, the X-ray telescope, the pipe, an iron 55 source manipulator that we will see later, that we were using to take calibrations on a daily basis. And as you see, the iron 55 source is close to the detector, but it doesn't go through the X-ray telescope. Okay, so these calibrations don't take into account the X-ray telescope, just are used to calibrate. Yeah. This one. There's a part about it, about the software we used. Yes, I will. No, sorry, yes, sorry, I didn't explain this. We were positioning a source here at the beginning of the magnet, yeah, an X-ray source. So these X-rays were crossing all the magnet. Sorry, I think this is funny. And that's why we were able to see how it was focusing the signal and to make sure that it was really centered and that everything was working as expected. Yes. So this kind of calibration, we did it once at the beginning, and then the other calibrations, which were daily, were without the telescope, because in principle this didn't move. We also had these targets that we call that with the geometers we could measure their position, so we were sure that it was all in the position it should be. Okay, so here just another image of the shieldings. Here we can see a little bit better the Vito panel, which is just above the detector, which is below in this box. Here's the box in the process of being closed with LED. And here the electronics that you see, the yellow case here is the same as here, which are closed in the Faraday cage. So this was all the shielding that we were using. And well, one of the most important things was the need for a gas system upgrade. As I said before, we were using argon, which it can be used in what we call open loop, so that we just flush argon at 2 liters per hour, for example, into our chamber. And once it goes, we just throw it away. But Shannon, it's too expensive to do that. So in Shannon, we really need to recirculate, but we need to keep this gas clean. So because there's outgassing, there might be moisture, there might be oxygen, many things that make the gas not transparent and would affect our data taking quality. So we had to design recirculation system. So the chamber would be up here. So the gas that is in the chamber comes out, it goes to our recirculation pump that it's always at a flux that we fixed, usually between 2 and 5 liters per hour. We have a gas buffer that we were able to keep there of a volume of 5 liters. And when the gas comes back, it passes through 2 filters that here they were still not installed, but they are these 2 for moisture and for oxygen. So in principle, with that, we were able to have a clean Shannon, even if we were having to do injections every now and then, but in principle, Shannon could be reused. We found that these filters, especially the moisture filter, is a radon emitter. So it can introduce alphas into our background. We are still studying if these alphas have a relevant contribution to the low energy background or not. But well, in principle, alphas are very high energy, so they shouldn't be directly a problem. But well, this is something that we learned and we have to keep in mind and see how to deal with this. All this installation was not free of challenges. Getting gain, getting proper data was very challenging, as all these things usually are. But well, what else about hardware? Well, for me, the most important part, the ultra low background detector. We are using a microbulk micromegas detector. These kind of detectors provide a very homogeneous gain and an amplification gap. They are intrinsically radio pure because they are made of copper mainly, and then we have like some shieldings with wait, I don't find it, sorry. Kapton, Teflon, all these kind of materials. They provide very good energy and spatial resolution. And we have a pixelized readout, which helps us see how the event looks like, the shape, the topological signature of the event, which is for us very, very important. Well, in our case, this is the exact micromegas that we were using. This is the readout, which is 6 centimeters times 6 centimeters. It consists of 120 strips in the X direction and 120 in the Y direction. So we only have to read 240 channels. Instead of having all individual pixels, we just have 240 channels. And they are mapped to this connector to the electronics. Here you have how we position the chamber on top of the micromegas. So here we would have the gas volume, and this gas volume is just a 3 centimeter chamber in which we, from the vacuum pipe, which is this pipe, we would have the X-rays coming, interacting in the gas, they convert in this region, and then we have a very small 50 micron amplification region in which we apply a very strong potential. And here, well, these voltages are more or less representative of the voltages we were using in this experiment. So these signals, when they reach the strips, we analyze them with the Rest for Physics framework that I would talk about later. And this is how we produce this kind of maps of events. Here, for example, we have a calibration with an iron 55 source that was positioned here. So this is like the daily calibrations we take. And as you see, there's an X-ray window that separates the vacuum from the pipe from the pressurized chamber. And here we can even see the shade of the window. So we are able to reconstruct things pretty well. So about the daily calibrations that we were taking, they were very useful for data quality control, because they give us, for example, the gain that we are getting that day, the energy resolution. So for example, here I plotted together all the calibrations taken with argon during 6 or 7 months, all already calibrated in energy. They are iron 55, so we have a peak at 5.9 keV and an escape peak from argon at about 3 keV. If we plot them all together, they are all calibrated, but in the energy that we get from the strips directly, we see that it's not always in the same position. This helps us see how the gain evolves. And so if we take this and we just see where each of the peaks is and plot it against time, we see that our gain is relatively stable within a 5%. So our detector is able to work in very stable conditions, even if it's summer or winter, or if it's independent of more or less temperature, humidity, etc. This is the same plot, but for xenon. And just to remind you that each of these calibrations, it's not only the spectrum, but also the heat map, and we can really control how things are looking every day. But these calibrations are very useful to calibrating energy. They are in fact used to calibrate in energy the background that was taken that day, but they are more or less monochromatic. We only see 5.9 keV events. So to really know how X-rays looks across our energy range from 0 to 10, we cannot just assume that they all look like 6 keV events. So for that, we went to the X-ray lab at CERN, where we have an X-ray tube that we can use different, in these wheels, we have different filters and different targets, so that we can produce a more or less monochromatic X-rays of different energies. So here is all the line of the X-ray, and here we plugged in our detector with our electronics. It's exactly the same detector we had at CAST. We just took it from one place to the other. And here we were able to calibrate at 6 different energies in our energy range of interest. These calibrations are used to describe how X-rays should look like in each of these energy ranges, and to be able to discriminate background from possible signal or from X-ray-like events. This, for example, this is just an example of how things really can change from one energy range to the other. This is just the resolution of the peak. But as you see, our resolution at lower energies is not very good, whereas at higher energies, we have energy resolutions below 20%. So all these things have to be taken into account, and the daily calibrations of iron 55 were not enough for this. That's why we did this kind of calibrations. And well, okay, now we have all the data. We were able to take all the data, make everything work, but now we need to analyze it. For this, we use a software that we are developing within the collaboration, which is called the REST for Physics framework. REST, which stands for Rare Event Searches Toolkit. Initially, it was Rare Event Searches with TPCs, but now we have opened it to a wider possibility of experiments and detectors. It's a collaborative software that it does data acquisition, data analysis, and also data simulation. So we try to unify everything in a single framework. It's written in C++ and it's fully integrated with root. I'm not sure if you are all familiar with root or not. It's the typical CERN software for particle physics and high energy physics. And well, it establishes a common procedure for output, input data format, for configuration files, so that we try to make it as flexible as possible and as user-friendly as possible. And it's also very important that we have now this GitHub repository. Everything is very well controlled, and we have official versions, so that we will always know which data analysis we have done with which version, so that we can always, or one external will always be able to reproduce exactly the same analysis. So everything is centralized in this documentation from GitHub. You can have a look if you're curious, or there's also a publication about REST where everything is explained. But of course, as usual, the best way of understanding it is using it and playing with it. But well, I'm going to try to explain what we do with REST, how we reconstruct the events. So what we get initially from the electronics, from here, the first row is a background event and the lower row is a calibration event. So in our electronics, each time one of them, so we had like the strips in our detector. And so, for example, if this strip and this one are triggered, we know that more or less the event should be here. This event in our electronics will give us one of those signals. Okay, with time beams here and an amplitude. So we have a lot of signals there because there were many strips triggered. And well, these signals, as we have this readout that we will see in other slides, we are able to position them in our XY plane and see where the energy deposits are. So we convert signals into events with X, Y, Z position and energy. This all goes into a root tree that we populate as we go through the analysis. And finally, we make the track events. So we decide if these energy deposits are all part of the same event or not, depending on the time where they happen, the position in which they happen, etc. So we do this for all calibration and background events. So we will have a root tree with all the information about these events. An example of a particular example of a run, yeah. The calibration event, it should be coming from the front, but a background event can come from anywhere. Yeah, so of course, cosmics come mainly from above. So in fact, we will see in some heat maps that there's an artifact precisely because that preferred direction. But in principle, a background, for example, an alpha that happens inside the detector could be in any direction. But well, that's one of the topological signatures that is very useful because if we see that, we know it cannot come from the pipe. So in that sense, it's very useful to disentangle events. So yes, this is an example of how we do everything from a calibration run. So as we saw before, this is our detector. We have implemented it in REST. We have this readout, but many other readouts from many other experiments, and any other readout could be implemented. So in our case, we have these 120 times 120 strips, making each strip 0.5 millimeters. And well, if you zoom in, you see like it's an intricate structure, but we have all this in REST. So we get activity in our channels, and we have a decoding file for each detector that translates this into really readout channels. So these are the X direction, and this is the Y direction. If you see this activity and you cross it, you already can imagine that it's going to be something like this, not something like this. So this is a calibration run. So using this information and the readout that we have implemented in REST, we can reconstruct a heat map for calibration. This is an event map for background. So here, for example, you see we have some excess on the sides precisely because of vertical, because the readout is not like that, but it's in this position. So if cosmic rays come from here, the mean position is going to be, okay, so there's like an artifact there. And we can reconstruct these heat maps, but also what we call the heat events, which is each energy deposit, where it is in the readout. From each energy deposit, we compute the mean position, and this mean position is what goes into the heat map. Okay, so we are really able to reconstruct the events pretty well. It's also important from REST, I'm a bit late, that we can use both experimental data and simulation data. And our idea is that at some point, they should be completely comparable. So from real data, we take the signal from the electronics. We are able to reconstruct them in terms of time and energy and position. So here we have time beams. This has turned into microseconds already. This full window is 10 microseconds. From the amplitude, we get the energy, and we are able to get a Higgs event. We can do simulations with G and 4. we have a Gen4 event, and with rest, we can see apply diffusion effects and see how our detector would see it. We can reconstruct the signal, what would be the signal, and here at this point, we are already at the same level, even if it's calibration or simulations. And if we apply the readout effects, for example, we see that in this from another experiment that they had a stripped readout, we see clearly the effect of the readout. So it's very important that both things at some point, they can go together, and the data analysis can be the same for simulations and for data analysis. So all this is to be able to identify a background and calibration events. This is a very clear event that would not be an X-ray. A calibration event would be something small, point-like, symmetric, okay? And so we can use different kinds of selection algorithms, mainly energy cuts between 0 and 10 keV. Above that, we don't care, as we saw before from the solar action spectrum. What we call the fiducial cut, we only keep the events in the center of the readout. Then all these topological cuts that about the shape of the events, etc., and the Veto event coincidence cut. So if we have an event in our micromegas like this one, which consists of a lot of signals, but just before we have a signal in the cosmic scintillator, we can assume this was a coincidence. This event was caused by a cosmic ray, so we remove it. In fact, if we plot all the Veto signals together, we see that we get a muon peak at 10 MeV, which matches the thickness of our scintillator, which is 5 centimeters. And muons in this density typically deposit 2 MeV per centimeter. So this is our muon peak. And we can remove many events that are caused by muons. So using all this, it brought us to the background computation and the expected limit. This is the preliminary background spectrum that we have achieved. We have in blue and green results with argon, that we see that here at 3 keV, we have the argon escape peak, and in red, we have the background with xenon. So it's very important that we don't have this peak anymore at 3 keV, which is where the Primakov produced actions would have the expected energy. As I said, this energy spectrum, it's only the central part of the readout. So from all these background events, we are only taking into account these ones, which go from -10 to 10 millimeters. And this is the same area of the readout from -10 to 10, and showing the focal spot, which is even smaller than the area in which we are computing the background. Okay, but then we have more statistics and we can always play with this. But of course, any axion candidate should be in that focal point. Well, here are some numbers. Well, here I put this plot also because I think one can see more clearly the difference, how this 3 keV peak is not there anymore. This is just before removing the cosmic induced events. And well, the background level is about 3 times 10 to the -6 counts per keV per square centimeter and per second in argon, and about 2 in xenon. But after the Veto cut, both are very similar, because we still have to optimize the electronics readout for the Veto cut in the case of xenon. But still, even if the background level is more or less similar, our efficiency is much higher. So what we care about is the figure of merit, as we saw before. So the background is similar, but the efficiency is higher. So the figure of merit with argon was a bit lower than with xenon. So in any case, even with all the challenges and the things that we've learned that we have to improve, we have been able to improve the figure of merit. Now the next step is just to add the slow control data. So to know if this event that looks like an X-ray was during tracking or not, when it happened, the precision of the pointing to the sun, because maybe we were doing tracking and the magnet was on, but the precision was horrible and we were not really looking to the sun. So we just have to make sure, select which data are under axion sensitive conditions, which are not. This will provide us with a background data set, a signal plus background data set, but we still need the theory, the expected solar axion signal. So for that, this is the step on which we are now, which I hope that the results will be computed relatively soon. So we have already this background and signal plus background. Now we have all these other ingredients that we have to correct our Primakov spectrum by the efficiency of our telescope. For example, the efficiency here is of xenon and neon plus the transmission of our particular X-ray window, which is made of mylar, which has some given thickness, etc. We also have to take into account that probably this is producing a shade, which is the strong back is producing a shade that will also reduce the efficiency. So, well, all this has to be taken into account. New code has to be written to analyze all this and get the expected limit for the axion photon coupling. And yes, well, this was all as a summary. I talked about the new data taking campaign with the IAXO Pathfinder system at CAST. We have doubled the statistics, so we will increase the sensitivity to the axion photon coupling. Most importantly, we have developed technology and know-how on how to use new gas mixtures based on xenon to remove this 3 keV contamination that we were getting from argon. We have found possible improvements, and we are testing them in new prototypes. It has been, in general, I can say, a very good experience towards the IAXO and IAXO. The background level is compatible with former results, and the new axion photon coupling will be computed hopefully soon. And yeah, that's all. Here I just leave a picture of the IAXO collaboration because they are all behind this work, not only me. So yeah, if you have any questions or anything, I'd be happy to answer them.
Thank you, Cristina. Do we have questions for Cristina?
Yes, but our efficiency at that energy is like, it doesn't exist. As it is now, maybe there are ideas, but as it is now, we wouldn't see anything.
It's not zero.
No, it's not zero.
In the beginning about the sensitivity of function of time, you may have said that as
Maybe Igor can explain it better than me, because yeah, I was not involved in the computation of that plot. So
yeah, but it's a line of
Think that line is the average after leaving Monte Carlo, possible Monte Carlo option. And the band is the spread, the maximum spread for the Monte Carlo. Everything always in the upper limit. And whatever was given to the level.
okay.
Thank you, Cristina, again.
Thank you.